So the first thing, I guess, always to do is to make sure the microphone's working. So the guys at the back can hear me? Good, okay. Second most important thing, Happy New Year to those of you who are celebrating Chinese New Year. Hopefully I got the year right. I just grabbed it off the internet. I think it's right. Okay, so I'm going to be talking about structured prediction for computer vision. Some of this will be a little bit of a review of graphical models that you saw, I think, on the first day by Justin. But then we're going to very quickly sort of go into some new stuff. Please ask lots of questions along the way. I'm going to try and remember to stop at points and ask you if you have questions. But if I forget to do that, just shout out the question. And yeah, I guess the last thing is that 3 hours is a long time to talk, so I'm probably going to make sense at the beginning, and then towards the end I'll start speaking a little bit of gibberish. And so that's probably when you want to start asking more questions, right? If you don't understand what I'm saying, stop me and ask a question. So structured prediction models are pervasive in computer vision. And what do I mean by structured models? Well, unlike, say just a supervised machine learning problem where you're trying to predict a single variable from some input, in a structured problem you're trying to predict multiple variables at the same time, and there's some sort of interaction between those multiple variables. So let's look at a couple of problems that are common in computer vision. One is a pixel labeling problem. So there are a whole lot of different variants of this problem. There's this type over here, which is interactive image segmentation. So there you're given an image, or the user's given an image. They scribble a few marks on the image showing bits of the image that's foreground, parts of the image that's background. An algorithm then goes away, builds a foreground-background color model, and segments the image into foreground and background. Okay, and so you can see here the red squiggles are where the user's marked foreground, the blue squiggles are where the user's marked background, and then the algorithm's gone and figured out how to segment the entire foreground from the background, right? And if the algorithm gets it wrong, it's interactive. You can go and scribble a few more places and rerun the algorithm. Another type of model is semantic segmentation, and that's where I do a lot of my work. So here, what we're trying to do is for every pixel in the image, we're trying to predict a class label for that pixel. And clearly, there are lots and lots of variables that we want to predict, and there's some structure there, right? Sky pixels tend to be high up in the image, and they tend to be next to other sky pixels. Grass pixels tend to be lower down in the image and tend to be next to other grass pixels. And so we can exploit that in a structured model. You can do the same thing for geometry, where instead of trying to predict the semantics of a scene, you're trying to predict the geometry of a scene. So is a pixel on a vertical surface or a horizontal surface or sort of back at infinity in the sky? And there are a whole lot of other problems where you're trying to label pixels. So image inpainting, stereo reconstruction, and so on. There's another class of problems where you're trying to detect objects or do pose estimation. And so these are slightly different in that you're not trying to predict a label for every pixel, but you're trying to locate a part or a bunch of parts on the image. So the classic example goes back to 1973, this face detection model where you know that a face is composed of two eyes, a nose, a mouth, some hair, and some ears, and these parts are all located at some relative location to each other, some relative position. So you expect to find the eye sort of next to each other and above the nose. And the structured model takes that into account. More recently, there are these deformable parts models where, again, you're looking for parts, and these parts are oriented relative to each other. And if you're trying to do pose detection, similar sort of thing, right? A human's made up of arms and legs, and all of these parts are connected to each other via joints. Okay, and finally, in sort of more holistic scene understanding, where you're trying to understand a whole lot of things about the scene, you're trying to understand the semantics and the geometry and the pose and all of these things at the same time, you can build up these structured models on top of each other. Okay, and all of these models have the same sort of flavor in that they're all based on these structure prediction models or Markov random fields. And so here's a graphical representation of these models. I'll go into the meaning behind these representations a little bit later. But basically, you have nodes for every variable that you're trying to predict, and these nodes are connected together if there's some sort of statistical relationship between the output labels for those nodes. And so pixel labeling problems tend to be grid structured, where you have one node for every pixel in the image. Object detection and pose estimation, you have a node for each of the parts or each of the joints that you're trying to predict. And then general scene understanding problems, you have these arbitrary graph structures. Okay, so It's early in the morning, I know, but I thought I'd get everybody to, well, a few of you to participate in a demonstration. So I'm going to call for a few volunteers in a sec. And what I'm going to demonstrate is a pixel labeling problem where we're trying to construct a digital montage from a set of photos. Okay, so the setting is that you're at a big family gathering or that you're attending a machine learning summer school and somebody wants to take a photo of the entire group, right? So what typically happens is you just take lots and lots of photos and you look through all of them to try and find the best one. And you're never going to find one where everybody's looking at the camera, right? So this is a really cool application where you can take a set of photos and then, like the interactive segmentation algorithm, you scribble a few marks on some of the photos to say, you know, I want these pixels from this photo and these pixels from another photo. But the key thing is you don't have to do that everywhere, right? You just do that on a few pixels. And the algorithm goes away and produces a synthetic image composed of parts of the image, parts of the photographs that you've taken, right? And hopefully you get something where everybody's looking at the camera. So I'm going to call for 4 volunteers. No volunteers. Come on, 1. Okay. 2, 3. 1 more person. 4. Okay. If you guys can come up and line up here, I'll just set the demo up. Okay, good. Hey, Peter. Okay, so if you guys face this way, face me. All right. It's always dangerous running live demonstrations, so I'm going to set this up so that it works properly, right? Just to drive home the point. So what we're going to do is we're going to try to take a photograph of these guys, okay? But they're going to be very uncooperative. What's going to happen is for each of the, I'm going to take 4 photos. For each of the 4 photos, 3 of these guys are going to be facing the back and only one's going to be facing forward, right? Okay? And then we'll try produce a photo where they're all facing forward. So we'll start with Nathaniel. Okay, you facing forward, everybody else face back. Okay, I'm going to take the first photo. 1. Okay, Nathaniel, you turn around. Peter, you face forward. Face the back. Okay, 2. Okay, next person. 3. Okay, and last person. 4. Okay, great. So thanks, guys. You can sit down. Okay, nothing's happened yet. You shouldn't be clapping. Right. So if I were to go through my photo collection, these are the 4 photos I have, right? Not very good. There's nothing there that I can really choose. But what I'm going to do is I'm going to say, well, I want this part of this photo, I want this part of this photo, I want this part of this photo, I want this part of this photo. Okay, very few pixels that I've actually scribbled on. Algorithm goes away and produces, okay, it's not perfect, but we can go back and okay, it's fixed it up, right? All right, so we've now got a photo where everyone's facing forwards, and no? Whose legs? Okay. And, okay. If I look at, oh, okay. So this is now showing us a map of which pixels are being copied from where, right? So this is the actual labeling that the algorithm's thinking of. And so it's labeling all of these pixels as, you know, red from the red image, these ones as green, those ones as blue and yellow, and we can see that, yeah, we got the bottom part of the yellow person wrong. I'm sorry. Okay, so the important thing about okay, so the important thing about this algorithm is that we've got this fairly large image, right? So we've got about 300,000 pixels that we're trying to infer. We're trying to label 300,000 variables. There's 4 possible labels per pixel. So the total number of ways that we can label all of these pixels, the total number of synthetic images that we could generate is 4 to the 300,000. Anybody know what that is? Quickly? Okay, it's a big number. We were able to run inference on this crummy laptop in under 30 seconds, right, to infer an image that was a pretty high quality image. Okay, I got a few little things wrong here and there. But it basically was able to navigate the space of 4 to the 300,000 within 30 seconds and come up with a good labeling of the image. Okay, and that's what structured prediction models do for you. They allow you to explore these really, really large spaces and come up with a labeling with an assignment to the variables that is a good assignment within that space. All right, so a little bit more detail about what these models are. Structured models are sometimes called Markov random fields, undirected graphical models, Markov networks, Markov random fields, conditional random fields, structured predictions models. I'm not going to make any distinction between them, right? Some people get very hung up if you call a CRF and MRF for some reason. They're all basically the same thing, okay? So what are they? There's a set of observations that you make, and so you can think of the observations as just the color of the pixels in an image. And these are always observed, okay? So in my notation, X is always going to be observed. Y are going to be the output variables that we try to predict. And so there's a set of them. There's n output variables. They come from some label space. In this talk, I'm going to focus on discrete random variables. So all of the variables are going to be discrete. And then an important thing within these structured models is that we're going to define subsets of variables. And we're going to have functions over these subsets of variables. So I'm going to call those cliques. And I'm going to denote Y sub C as the set of variables within a clique, within some subset. Okay? And there's going to be lots of these different subsets, and they can overlap and so on. So now, given that we've broken the model or the variables into these cliques, we can define a factored probability distribution, which is the probability of some output, right, labeling all the variables in the output given our observations, is going to be the product of these so-called clique potentials. Okay? And the clique potentials are going to be defined over these subsets of variables. Now, the main difficulty in all of these structured models is that to get a valid probability distribution, we have to normalize all of the possible assignments to the variables, or the probabilities for all of those assignments, so that when we integrate this probability over all possible outputs, we get 1. This normalization constant, which is called the partition function, in order to compute that, we have to sum over an exponential number of assignments. Okay, so we saw in the photo montage example, there were 4 to the 300,000 possible assignments. And in order to compute this partition function, we have to sum over all of those assignments, right? So that's the difficulty. That's an intractable sum. And so a lot of the algorithms that we'll be looking at try to get around this intractability. Okay, that's the main difficulty that we're trying to get around. All right, so everyone's clear on the notation and, I guess, the definition of a factored probability distribution? No questions yet? Good. Okay. So then in these structured prediction models and in machine learning, I guess, more generally, there's really 2 tasks that we sort of care about. The first task is the learning task. So that's given a set of data and some problem specification. Can we learn the model, which means both the structure of the model and its parameters from data? Okay? And in this tutorial, hopefully at the end, if I have time, we'll get into some parameter learning. We won't talk about structure learning. And normally the structure comes from domain knowledge, but there are algorithms for learning structure as well. Okay, the other task is the inference task. So given a model, once it's fully specified, so its structure and its parameters are known, can we answer queries about the model? Okay, so can we infer the output labels? And most of the tutorial is going to be spent on this inference task. And the core inference task that we sort of care about most in computer vision is the map inference task. So here we want to find the most likely assignment to the variables. Okay, and so you can write that out as y star is going to be the argmax over all possible y's of the probability of y given x. Okay, so you're just finding the y that maximizes the probability. Now, if you go through this sort of sequence of steps, we first substitute in the definition, our structured probability definition for P of y, and then we can take the log of this structured probability, which will allow us to replace the sum, the product over here with a sum, okay? So the log of a product is just the sum of the log, all right? And now that we've done this, we notice that we have this term at the end here, which is the log of the partition function, and the log of the partition function doesn't include any variables y, right? It doesn't depend on our output labels. It's a function of x, of the input. And so in terms of inferring the most likely assignment, inferring the y with the highest probability, we can ignore this partition function. And I said, I guess on the last slide or a few slides ago, one of the main difficulties is in computing this partition function. So this is great, the fact that we can now ignore it in finding the most likely assignment to the y's. And so we left with this problem over here, which is to find the y that maximizes this sum, okay? And if we flip the sign of this, this is then called energy minimization in computer vision. So we define an energy function, E of y with an x, as the sum of these log clique potentials, okay? So I've taken the negative log of the clique potentials I had before. And then the probability, we can write this probability as equal to e to the minus energy function divided by some normalization constant, right? So then we arrive at what I said on the previous slide, that the argmax, so the map problem of finding the output that maximizes the probability, is the same as finding the y that minimizes the energy, right? So in computer vision, you hear people talk a lot about energy minimization, and that's exactly the same as map inference in the statistical sort of literature. So these two y's? Oh, z? Yes. No, it's the same z. Okay. So to compute this z here, you basically have to sum, you first ignore it. You sum over all possible values of y, computing this expression, and then you divide by z, right? And that ensures that when you sum over the probabilities, you get 1. But you'll notice that the z appears here because you have to substitute this expression into the argmax. It doesn't appear here for the energy, right? So you can ignore it. Okay, so let's talk a little bit more about these clique potentials. I've said that there are these abstract sort of clique potentials that map from a subset of the output space to these real numbers. And what they do is they encode a preference for assigning values to subsets of random variables, right? So if going back to the semantic segmentation problem, if I have a single pixel in an image and it's high up in the image, then it's more likely to be sky than ground, say, right? So I can define a clique potential over that single pixel, right? So in this case, it's a singleton clique. It's only got one variable in it. That gives a lower score for assigning sky to that pixel than assigning grass or ground to that pixel, okay? And so you can do this for all the different cliques in your model. They assign these preferences, and they're often parameterized as a dot product between a weight vector and a feature vector. And this is important when we get to learning, okay? For now, you could just think of the clique potentials as big lookup tables. So I have a subset of variables. I assign values to that subset of variables, and then this lookup table tells me the value of the clique potential, right? And it does that for every possible assignment to the subset, okay? And what I'm also going to do, just to simplify things, is ignore the explicit conditioning on x. So I'm going to assume that built into the definition of the table, you've already taken into account the observations. All right. So an important distinction with these clique potentials is the arity of the potential. So we've said that the energy function can be written as the sum of these log cliques, clique potentials or terms. And we can categorize those as unary terms, pairwise terms, and higher order terms, all right? So unary terms are going to be potential functions that are defined over a single variable. Pairwise terms are going to be defined over 2 variables. And then higher order terms are defined over 3 or more variables. And in a lot of computer vision, we build models that just have unary and pairwise terms because they're easy to deal with, okay? And so here is a typical representation of a model with just pairwise terms. We have the output variables as these white nodes and the observed variables as these colored nodes. And for every edge in the model, there is a clique potential. So here, just on the variable, say, y1, there's a unary potential over this variable which may or may not take into account the observed x. And then between pairs of variables, because we have an edge, there's a pairwise clique potential between those, okay? And you've probably seen this in the first lecture on Monday, right, on graphical models. All right, so let's talk a little bit about where these potential functions come from and a little bit more about the types of models in computer vision. So for the semantic segmentation problem, I said what we wanted to do is label every pixel in the image with a semantic class label. So the label space for every pixel is going to be this set of possible labels that we know about, so sky, tree, grass, foreground object, and so on. And then we're going to define these unary potentials, which we're going to derive from a independent prediction model, so a probability model that we build on predicting independently if a pixel is one of these class labels given the observed features in the image, okay? So for every pixel independently, we can build a classifier that says, how would you classify this pixel given just the features, so the color of the pixels that you see around it? And that goes into our unary potential. We have to take the log because the energy function works in log space. And then the pairwise potential is going to be defined between any 2 adjacent pixels. And we know from looking around us, the world tends to be smooth. Images tend to be piecewise smooth. So what we'd expect is, given no other information, 2 pixels that are next to each other in an image should take on the same class label, right? You'll find if you have 1 pixel that's sky, then it's highly likely that the pixel next to it is also sky, okay? And so we have these contrast-dependent pairwise terms, which, if we just ignore this contrast term at the moment, so just look at the first part, what this says is that if the 2 variables take on different labels, so if yi doesn't equal yj, then you pay this penalty term lambda 0, okay? Otherwise, you pay nothing, right? Now remember, we're trying to minimize the energy. So if I have a labeling where yi is different to yj, I'm going to pay a penalty. If yi is equal to yj, I'm not going to pay a penalty, and so the model is going to prefer labeling adjacent pixels as the same label, right? Now, of course, it's got to trade that off with all of these unary potentials, which may be trying to label things differently, okay? And so in inference, you need to take all of that into account. The second term here is a contrast term, and so what that allows you to do is to strengthen or weaken this pairwise term, this preference for labeling pixels as the same value, depending on their features. So if they have similar features, then you'd expect them, and they're adjacent to each other, then you'd expect them to be the same label. If they're at a contrast boundary, so they're on an edge of an image, then you may relax that penalty and allow them to take on different values, okay? Here's an object detection model. This was and still is a very popular model for object detection, known as a deformable parts model. So here you have a bunch of parts that you're trying to place on the image, and those parts are going to come together to tell you where the object is. So the label space for each of the parts is going to be its location in the image, so its x and y coordinate, right, which is going to be between 0 and the width of the image and 0 and the height of image, plus a scale, right? Objects can appear at different scales. So it's a pretty large label space. The unary potentials are going to be part detectors, and they tend to be filter responses. So you model the part as a filter, you run that filter over the image, and that filter is going to return a score which tells you how well the pixels underneath the filter at that location match the filter itself. Okay? So that gives you your unary potential, and then the pairwise potential is a deformation cost, right? And what that does is it says, well, I know from my training data that parts should appear at certain locations from each other, relative locations to each other. I'm going to allow those parts to move away from each other a little bit, but I'm going to start penalizing if they move away too far, okay? And so you have this quadratic cost function that the further you are away from your expected location to each other, the higher the cost you pay, right? And there's going to be some offset terms in there to allow the parts to be offset from each other. Okay, final example, the demonstration we saw. Here, the label space is the index of the image that I'm going to copy the pixel from, right? So if I have k images, the labels are going to be 1 up to k. And then once I've got the labeling, I can just copy the pixel colors across. The interesting thing about this model is there are no unary potentials, right? There's no sort of model of whether a pixel should be included in the image or not based on that pixel alone, right? Except for the ones that I've colored over. They're forced to be part of the synthetic output image. But there is this seam penalty, which is a pairwise penalty that prefers adjacent pixels to be both included or both not included in the output image if they have similar features, so if there's no edge between them, right, in a similar way to the pairwise term, okay? And so what that does is it allows the algorithm to find good seams in the image where it's going to switch from copying one image to another image, and then your eye can't see where that boundary occurs, right? You get a nice looking image at the end. All right. So the exact form of these potential functions is not really important. The main thing is for you to just get a flavour of the different types of potentials and how you can construct them for any given model. Okay, so I said before that structure prediction models are sort of the same as graphical models or as undirected networks. You probably saw in the first lecture on Monday that we can depict these models in a graphical way, all right? And so if we have this example energy function over here over 4 variables, y1, y2, y3, and y4, let's say we have pairwise terms between pairs of variables, so a term between y1 and y2, between y2 and y3, and so on. So we can draw that graphical model in this way, where we have a node for each of the variables and an edge between any 2 variables that appear in the same clique potential. Okay, so here's a function over y1 and y2. We draw an edge between y1 and y2. Another way to depict this model graphically is using a factor graph, right? So here we have 2 types of nodes. We have circle nodes, which represent the variables in our model. And then we have these square nodes, which represent factors. And so this square node represents the first factor or clique potential. And we put edges between a variable node and a factor node if that variable appears in that factor. Okay, fairly straightforward. And so this is a bipartite graph. The variables connect to the factors connect to the variables, but there are no edges between them. All right. So let's look at this example over here. So here I've got an energy function which is defined over, let's say, all pairs of variables, right? So now, in addition to the edges I had before, I add these diagonal edges to my graphical model representation. Because y1 and y3 are going to appear in a factor together, and y2 and y4 are going to appear in a factor together. Okay, you may have noticed that I've switched from saying clique potential to factor. Okay, they're the same thing, so don't let that confuse you. Okay, and here is the factor graph representation. So again, I've got the same factors I had before. I've got an additional 2, and I add those edges, right? Now, here's a different energy function. So the energy function on the previous slide was the sum of these pairwise factors or pairwise potentials. here I've got an energy function which is defined over one big clique. It's defined over all of the variables in the model. The graphical model representation looks the same. I put an edge between any two variables that appear in the same clique. The factor graph representation looks very different. There's only one factor, and that has edges to all of the variables. Okay, and so there's ambiguity in the graphical model representation. There's no ambiguity in the factor graph representation, and for that reason, a lot of people prefer factor graphs to the standard graphical model representation. For me, the graphical representation is sort of nice. It gives you a feel for what's going on. But it's much more important to look at the form of your energy function, right? The structure of your energy function and looking at the various terms in your energy function allows you to develop algorithms that exploit a lot more of the structure than just looking at these graphical representations, okay? So don't get too bogged down in the graphical representations. Look at the structure of the energy function itself. Okay. So we've said in computer vision, something that we really care about is energy minimization or map inference. Okay, so this problem here of finding the assignment to the output variables y that minimizes the energy. Now, some structures, some graphical structures, admit tractable inference algorithms. So in particular, if we have graphs with low tree width, and I'll define that a little bit more formally in a sec, we can use message passing algorithms. One of the big impacts in computer vision, probably in the last 10 years, or starting from about 10 years ago, is that if we have energy functions which have a particular property known as submodularity, then we can use graph cuts to infer the output labels very, very quickly. And I'll go through the graph cut algorithm later in the tutorial. Okay. So if you have an energy function with either of these two properties, then you can do exact inference very, very fast, right? And you saw me doing a variant of that when we did the demonstration with the photo montage. If your energy function doesn't have these properties, then not all is lost. We can resort to approximate inference algorithms. And usually these approximate inference algorithms give us very good solutions. Sometimes they do it with certain guarantees, sometimes without guarantees, but at least the algorithms exist and we can get an answer. And so we can run message passing on general graphs, not just low tree width graphs. We can use move-making inference, which is a wrapper procedure around graph cuts. And we can do linear programming relaxations. And so for the next part of the tutorial, I'm going to go through each of these different inference algorithms. Okay. Any questions up till this point? No. Okay. All right, so let's start with exact inference. So here again is a simple example. I've got an energy function. It's defined over 4 variables and 3 cliques. You can see the factor graph representation here. Okay, I've just moved things around a little bit so it fits in the slide nicely, but you still have nodes that are factors, nodes that are variables, and a variable. There's an edge between a variable and a factor if that variable appears in that factor. You can see this is a really nice structure. It's a chain model. Okay. And so what I'm going to do is I'm just going to represent that a little bit differently, where I'm going to group nodes together, variable nodes together into cliques if those variables appear in the same factor. Okay, so I'll just put y1 and y2 together, y2 and y3, and y3 and y4, and I put an edge between them because y2 appears in both of these cliques, and here y3 appears in both of these cliques. Okay. All right. So our inference procedure is to try and find the y that minimizes with minimum energy, right? So I can write that out this way. I want to minimize over y1, y2, y3, and y4 of this sum here, right? Now, notice that y4 only appears in the last term of the summation. So what I can do is I can push the minimization over y4 all the way to the end of the sum. Okay? And now all I have to do is minimize this function over y4. I end up with a function over y3, and I'm going to call that m C to B of Y3, okay? It's going to be a message from clique C to clique B, which is defined over the variable Y3. Okay? Now I can just repeat this procedure. So again, Y3 only appears in this clique here and this message, and so I can push that minimization past the first term to only take into account the second term. And I do the same thing. I minimize over Y3 for each value of Y2, and I end up with a message from B to A, which is defined over Y2. Okay? And then finally, I just have to minimize over Y1 and Y2. Okay? Any questions? Yes.
Is that an exact equality, or it's just kind of approximation?
No, that's an exact equality. Okay? So, so if we just look at these first two steps, right? For every instantiation of Y1, Y2, and Y3, okay, so let's say I hold those fixed, I need to minimize over Y4. Okay? In order to do that, all I really need to do is for every value of Y3, know what the minimizing assignment of Y4 is. Okay? That gives me a function over Y3 alone. It eliminates Y4 completely from the problem. And then I can just iterate, okay? And only search over Y1, Y2, and Y3. Yep.
So we have this Y2, Y3 in both these terms.
Yep.
So by separating this, does it always guarantee we have minimum for the last one, we always have minimum for the total
Okay, so the question, sorry, I was told to repeat the questions because maybe you didn't hear it, and also for the video. So the question, as I understand it, is Y3 appears in two different cliques, right? And, or in two different factors. And the question is, if I minimize over, I guess, one of the factors and minimize over the other factor, does that guarantee that I get the same Y3 for in the minimization? Right, no. Okay. So, so if I minimize independently, if I minimize over Y3 of just one of the factors, and I minimize over Y3 of the other factor, the Y3 that I get in each of these cases may be a different Y3. Okay? It may be that one of the factors prefers Y3 to take value 0, and the other factor prefers Y3 to take value 1. Okay? So I can't minimize independently. I have to minimize these things together. And that's what this allows me to do. This operation of pushing the minimization in says that over here I can do this minimization independently because that's the only place that Y4 appears. Okay? But once I've done that minimization, I have to combine these two terms together and minimize over them jointly. Okay? And then I get the value of Y3, which minimizes the sum. It doesn't just minimize each term independently. Okay? That's the very important thing in these structured models, is you're trying to find an assignment which minimizes jointly over all of the factors, so the entire sum, rather than each term independently. Okay? Is that clear? All right. So now, in order to get the actual assignment to the variables, I have to move backwards. Okay, so this is a dynamic program where I've reduced the problem and on the last line of the previous slide to just minimizing over Y1 and Y2. Okay, so I can find the argmin over Y1 of this expression minimized over Y2. I can then plug that value of Y1 back into the expression and then minimize over Y2. Okay, in reality, you would just do these two steps together. And then keep going back through the chain. So now I know what the optimal value for Y2 is. I can plug that into the expression that I had for the message from B to A and minimize over Y3. And then finally, find the minimizing assignment for Y4. Okay? So this algorithm runs in two passes. There's this backward pass that goes from the end of the chain, passing messages down to tell me how I need to do my minimization. And then there's this forward pass, which gives me the value of the variables. Okay? All right. So let's just have a look at what this has saved us, right? What we could have done is we could have just instantiated every possible labeling for the variable, so every possible assignment jointly to y1 through y4. And if we have a chain of length n, where each variable can take L labels, then this brute force evaluation, if we had to go and evaluate every possible labeling, would be the size of this label space, which is L to the power of n, right? L labels, and there's n variables. With this Viterbi decoding, okay, so if we have a chain of length L, and we do this forward and backward message passing, it ends up costing on the order of n times L squared, right? So L squared is a hell of a lot smaller than L to the n. We've saved an enormous amount of computation. And it turns out that we can even make further speed-ups by looking at the functional form of these factors. And so it's possible that for some factors, this operation reduces to linear in the number of labels rather than quadratic in the number of labels. Okay? But the main message here is we've gone from exponential in our number of variables to basically linear in our number of variables and quadratic in the label space. Huge, huge saving. Okay, so that's great. That works on chains. What about... Oh, sorry. Before we get into that, let's just look at the two main operations that we have to perform, right, in doing this algorithm. So there was an operation of factor addition, where we had to take a factor and a message, which is just another factor, and we had to add them together. And so this is an operation which generates an output factor. There should be a P there. An output factor whose scope, so it's defined over a set of variables, that is the union of the scope of its inputs. Okay? And each element of the output is just the sum of the corresponding variables projected onto the inputs. So if I have this operation that I want to perform here, I want to produce a factor C, which is going to be the sum of factors A and B. Well, that factor is going to be defined over the union of the variables that are in each of the factors, A and B. And to compute the factor's output, the value of the factor on any assignment, I'm going to take the sum of that assignment projected onto the variables of the input factors. This will hopefully become clear in the next slide. I'll show an example. The other operation we had to do is factor minimization. So here what we want to do is we want to take an input factor or multiple input factors, and we want to remove variables from those input factors by minimizing over those variables. Okay? So the output now is going to have a smaller scope. That's going to be a subset of the scope of the input. And I'm going to define the value of the factor for each particular labeling as the minimization over all of the variables that I'm removing, fixing the other variables to that particular assignment. Okay? And so if you can do these factor operations quickly, you can run a lot of these message passing algorithms. Almost all message passing algorithms are based on these type of factor operations. Okay, so here's just a worked example to really drive home the point. Okay, so I have this factor A, and I want to add it to this factor B. I've represented them as just this table. So they're over these binary variables, y1 and y2 here, and y2 and y3 for factor B. So if the variables y1 and y2 both take value 0, then the value of this factor is 1, right? The summation is going to be defined over the three variables, y1, y2, and y3. And so if I take any row over here, let's say I take this row, okay? So y1 is 0, y2 is 1, and y3 is 0. So I look over here at the 0, 1 configuration for y1 and y2. So 0 and 1 gives me 4 from that factor. Okay, so that's the 4. And then 1 and 0 for y2 and y3. 1 and 0 gives me 1. So 4 plus 1 is 5. Okay, very straightforward. All right. Okay, so we've shown that we've got this great message passing algorithm that works well on chains. It takes us from an exponential inference algorithm down to an inference algorithm that's quadratic in our label space. It turns out we can generalize this algorithm to run over trees. And so what I'm going to do is I'm going to define something called a clique tree or tree decomposition for a particular energy function, and that's defined as this pair where the first element of the pair is a subset of cliques. Okay, so it's a family of subsets of variables, 1 to n. And the second element of this pair is a tree defined with nodes, which are these cliques, and the tree has to satisfy 2 properties. The first property is called the family preserving property. So what that says is if I have a factor in my energy function that's defined over a subset of variables, it's defined over a clique, then that clique must be a subset of at least one of the cliques in my clique tree. Okay? And then the second property is called the running intersection property, and this says that if I have any 2 cliques in my clique tree that share a common variable, then there needs to be a unique path in the tree between those cliques where every node on the path also contains that variable. Okay? So you can think of this as you can't have a variable appearing in 2 disconnected paths of the clique tree. All right? If you can build a clique tree with these properties, then running this message passing algorithm that I described before over that clique tree will give you exact inference. All right? And so in particular, if you have an energy function which is already defined as a tree, such as the pose model that I showed at the beginning, then you can run exact inference on that algorithm. Your graphical model tree is the same as your clique tree. Okay, and so what do you have to do? Well, this is the basic model, algorithm. You first sort your nodes in some topological order. So you sort your nodes in order, and then you start sending messages in the reverse order to your topological ordering from a clique I to its neighboring clique J, which is the exact calculation that I showed in the chain. So you take the clique for the particular node that you're sending the message from, you add to it all of the messages that have come into that node already, okay? And if you're the first node in the ordering, you don't have any messages coming in. You add those together using the factor addition operations, and then you minimize over all of the variables that don't appear in the node, in the clique that you're sending the message to. Okay? And that gives you a message over the intersection of the variables that are in those 2 cliques. And you keep doing this through your reverse topological order. Okay? Then you decode your energy by sending messages in the other direction, right? Where you, again, now take your clique potential and all the messages that have come into that clique potential. You add those together, and then you find the minimizing assignment for each node. And this particular term here is called the min marginal. Okay? And the only thing you need to be careful about is that ties need to be decoded consistently. So if you have 2 possible values for yi, which are both minimizing values, then you need to decode those consistently with your neighbors. And you can do that easily by just propagating that value backwards through your tree in the same way we did it in the chain. Okay. Is that clear? Somewhat? No questions? Okay. All right. Yes.
Do I understand correctly that you're sending, so you're first assuming that y1 has some value, and then this value being fixed, you're asking what are the other values, and then you iterate.
When you go backwards, yes. When you do this first pass, you're building a table for all possible values of y1. You say, what would be the value minimizing over y2, say?
So you iterate over all possible y1 values, and you're asking for each of them what's the minimum over all the rest?
Yes, yes, yes.
So why is this?
Okay, so just so that everybody else can hear, the question was, when you're sending these messages, do you fix y1 and then send the message, or do you compute an entire table over all values for y1? And the answer is you compute the table. So in this case, instead of y1, let's look at y3. Here, we have this. You can think of this as a two-dimensional table, right? For every value of y1 and y3 and y4, the factor produces some output. It has some entry in the table. What we're going to do is we're going to take this from a two-dimensional table, and we're going to construct a one-dimensional table, which is indexed by y3. And for each of the elements in that table, it's going to be the entry from this table with the same value for y3 and then minimized over y4.
So why is this? Why is the complexity as shown? Why is it n times?
Oh, okay. So what you have to do is, in order to do this minimization, to produce this table takes L squared operations. You have to look at every entry in this table, which is L squared. Okay, so for every, let's say we have for every row in the table, so for every value of y3, we need to go along and we need to find the minimum value in that row. For one row in the table. Okay, so that's going to cost us L to scan through that row. Now we have to do that for every row. There are L rows, so that's going to cost us L squared. Okay, and that allows us to produce this message.
Yes, but it's having all the rest fixed, right? All the other variables.
Well, the other variables don't come into play here. The only variables that we need to consider here are y3 and y4.
Yes, but if they change,
Well, if the other variables change, it doesn't affect this minimization. So that's the beauty of this algorithm. The only value that affects the minimization over y4 of this final term is the value for y3. And so we've now captured that by having this new function, this new table that's defined only over y3. Okay, so each of these operations going from here to here is L squared, and then we have to do that n times through the chain. Okay. Yep.
So we just fix the minimum for each variable at each step, and what happens for y1? So we can start with y12 and find the minimum of 1, 2, then go to the second one, and then go to the last.
Yeah, so the question is, when I'm doing this operation over here, what happens to y1 and y2, right? And the point of this algorithm is it doesn't matter. It doesn't matter what y1 and y2 are. I'm not fixing them to any particular value. What I'm doing is I'm saying I can replace, because I know that at the end of the day I want to minimize over all these variables, including y4, I'm going to replace this function that's defined over y3 and y4 as a function that's only defined over y3. And I'm going to have minimized out y4 for each of the possible values of y3. And it doesn't matter what y1 and y2 take. Okay? I'm going to keep doing this backwards through the chain. So the value that y3 takes is going to depend on the value that y2 takes. Right? But it doesn't depend on it at this point. It depends on it at this next step in the chain. So I keep going backwards through the chain, and eventually I get a function that's only defined over y1 and y2. And I know that if I minimize over that y1 and y2, that gives me the minimizing assignment globally over those two variables, and then I can take a step forward and find what the value of y3 needed to be for those to be the minimizing assignment. I can do this because it's a chain, and then I just showed that you can also do it because in trees, right? So if you have a clique tree, you can do the same algorithm where you just sort the nodes in topological order. Sorry. Oh, right, yes. Okay, it's possible. Okay, so the question is what happens if you have ties? So if when I minimize here, there are multiple values of y4 which appear as the minimum. They give me the same value of the function for a particular y3. Okay, the point is over here it doesn't matter, because over here I care about the minimum value of this function over y4 for every value of y3. And if that minimum value is the same, then it didn't matter which y4 I chose to get there. The point at which it does matter is when I go backwards through the chain. Okay, it doesn't matter on the last variable because I could pick any of the y4s and that gives me the same value of the energy function. But if I chose a particular value of, say, y2 earlier on, where I need to then choose a value of y3 which is consistent with that minimizing value of y2. Okay, so it's possible, let's say I have a model that says that an image should be completely uniformly colored, right? And I have black and white. I can color it each pixel either black or white. Then what the model is going to say, if I give it a completely black image, it's going to say, yes, that's the minimum assignment that I can give. If I give it a completely white image, it's going to say the same thing. That's a minimum energy assignment to the variables. But if I try to label each variable independently, if I label half the pixels as white and half the pixels as black, the model is going to penalize that. That's not a minimum energy assignment, right? Even though white pixels or black pixels appear in a joint assignment that does have minimum energy. So if I had a problem like that, when I went through the decoding, I would pick my first pixel. I could say, well, I can either label this pixel black or white. I choose one, right? Choose black. The next pixel I label then has to be consistent with the labeling I've already chosen. And that's what this algorithm does. It instantiates the label I've already chosen, and then it tells me to minimize the function once I've got that label. And that will give me an image which is all black, right? Okay. Yes. Y4 can't change in the meantime. I'm only going to look at Y4 again once I've got the labels for all the other pixels. Okay, so I do that's why I have to do this on a chain. Okay, there's a particular order in which I have to send messages.
Do I understand correctly? It's just dynamic programming, and there's just backwards. There is no forward step, right? You just go from
The forward step is in computing these messages. Okay, so the question was, is this just dynamic programming? Yes, the answer is yes. It's just dynamic programming. You have a forward step where you're computing the energies, and then a backward pass where you pull out the assignment. Okay, and it turns out that what works on a chain also works on a clique tree. Okay, and you can then do the exact same algorithm on a factor graph, where now instead of sending messages between cliques in a clique tree, you're sending messages between nodes and factors, right? And between factors and nodes. Okay, and so here there's a message from a variable node to a factor, which is basically the sum of all of the messages from other factors into that node. And then there's messages that go from factors to variables, which are exactly the messages that we saw before, where you can think of the variable as a singleton clique, right? And so the main point here is that there's no real distinction between clique trees and between factor graphs. As long as you can arrange your factor graph in a tree, you'll have an exact algorithm. Okay? Now, everything I've said up to this point about exact inference only works if you have a tree-structured graph. But the algorithm, the messages that you pass, are well defined over an arbitrary graph. And so, okay, so first of all, if your graph is low tree width, you can still perform exact inference. And there's an algorithm known as a junction tree algorithm, which will take an arbitrary graph and produce a clique tree from that graph. So it'll group nodes together until you end up with a tree, so you don't have any loops within the graph. What may happen is you may need to group too many nodes together, such that when you try to define a factor over that group of nodes, over that clique, it's too large, right? It becomes exponential in the number of variables in that clique. And so if you can't do that, you can send messages anyway because the messages are well defined. And this is known as loopy belief propagation. It's an approximate algorithm. Because you don't have a topological ordering in an arbitrary graph, there are a bunch of different message schedules that you can come up with for how you're going to send the message and how you initialize the messages. But basically what you do is you have your nodes in the graph and you pick a first node, and that node sends a message to all of its neighbors. And then when those neighbors receive a message, they combine those messages with its own factor, and then computes outgoing messages to its neighbor nodes. And you just keep sending messages, right? And there's no guarantee of convergence, so you can keep sending these messages. There's no guarantee that the messages will actually converge to something. But these algorithms tend to work quite well, and variants on the algorithms can be made to converge. When they do converge, they don't always converge to the right thing, okay? So you might be sending messages around for a while. Eventually, all your computations end up being the same. So you compute a message a second time is the same as the message you computed the previous iteration. So you've converged to something, but when you then go and decode your labeling, that may not actually be the minimizing assignment. And that's because the problem is NP hard, right? We can't hope to come up with an algorithm that with all possible scenarios will give us the minimizing assignment. But in practice, this works quite well. Sorry, there's a question?
Sorry, I was just going to ask, so I'm trying to imagine in my head how this works. You've got this problem of messages possibly going everywhere. So is a necessary condition for the schedule that one node should only have at most one incoming message at a time? Or do you just, how do you handle multiple messages potentially coming at the same time? Do you just disallow it, or is there something different there?
Okay, so the question is, how do you handle, I guess, the coordination of messages between nodes? What happens if a node receives either one message or multiple messages at the same time? Usually what you're doing is you're running this on a single machine. It can be generalized to a cluster, but normally you're running on a single machine. So you're only actually computing one message at a time. And you will send that message to a neighbor, but in actual fact, that message just sits in a queue until your single process gets around to processing it. And so in actual practice, you're only processing one message at a time, right? Or you're only computing one output message at a time. Now, you can actually run this asynchronously on a cluster, and different machines within the cluster are computing messages on different nodes. And the point is, in some sense, it doesn't matter. I mean, you can process a message whenever you receive it, or you can wait until you get all of the messages from all of your neighbors and then compute an outgoing message. Different variants of the algorithms may or may not have different guarantees depending on the structure of the graph, but in general, it's an approximation algorithm, and there are no guarantees. All right. So we've got, I think, about 25 minutes before the break. That was the first class of inference algorithms that I wanted to talk about. Message passing algorithms. The next ones, which are very, very popular in computer vision, are these graph cut-based algorithms. And I think we'll probably get about halfway through this before we end up having a coffee break. Okay. So again, let's just look at a motivating example for a binary Markov random field. So I'm going to construct this energy function. It's over two binary variables, y1 and y2. And I'm going to have three factors in my model. So the first is a unary factor over y1, second is a unary factor over y2, and the third is a pairwise factor over y1 and y2. And I'm going to define these factors by these tables here. So the first factor, if y1 takes value 0, it's going to return a value of 5. If y1 takes 1, it's going to give me a value of 2, and so on, right? Same here with the pairwise factor. If y1 takes 0 and y2 takes 0, I get it, the factor evaluates to 0. Okay? So I can write this energy function out in this form known as a Posi form. And a Posi form, I'm going to introduce negated copies of my variables, okay? So y1 bar is the complement of y1. So if y1 is 0, y1 bar is 1. If y1 is 1, y1 bar is 0, okay? So you can think of that just being 1 minus y1. Okay, so now I can write my first factor, psi1, out in this way. It's 5 times y1 bar plus 2 times y1. Right? So let's see what happens. If I stick 0 in for y1, then this evaluates to 0. y1 bar is 1, and so I get value 5, okay, which is the value of my factor. Okay? I can do the same thing for the second factor. It's going to be y2 bar plus 3 times y2. You can see that that gives me the same values as what's in the table here. And then finally, for my third factor, it's going to be 3 times y1 bar times y2. Okay, so this part gives me that entry there. 4 times y1 times y2 bar gives me this bit. And then the other two entries are 0, so they don't appear in this sum. Okay? So this Posi form is exactly the same as that table definition of my energy function. So just for completeness, here's the graphical model. There's just two variables with an edge between them. I can go and evaluate the probability table where for each value of y1 and y0, I've gone and computed the energy. So 0, 0 gives me a value of 6, okay, which is 5 plus 1 plus 0. 0, 1 gives me a value of 11, so 5 plus 3 plus 3. Okay, and so I can go and do that for all of my energies, and then the probability is just e to the minus energy normalized, so that it sums to 1. Right, so you can see that the highest probability assignment is this one here, 1, 1, according to my model, and that's also the assignment that has the lowest energy. Right, energy minimization equals MAP assignment, most probable assignment. All right. So in order to understand the graph cut algorithm, we need to understand these functions known as pseudo-Boolean functions. So a pseudo-Boolean function is just a function from a fixed length vector, Boolean vector, to a real number. That's called a pseudo-Boolean function. It's pseudo-Boolean because its input's Boolean, but its output is real, right? It would be a Boolean function if its inputs were Boolean and its output was Boolean. So a pseudo-Boolean function can be uniquely represented as a multilinear polynomial, so a polynomial that only has linear terms. And the function, the energy function that I defined on the previous slide can be uniquely written out in this way. There's an alternative representation, which is known as a Posi form, where I introduce these negated copies of the variables, right? So the y and its complement. And I can write out the energy function or the pseudo-Boolean function in this way, where every coefficient is non-negative, right? And the 0, 1s you drop. So every coefficient is positive, except for the possibility of a constant term out the end, which can be negative. And so I can write this function here in this way. And if you evaluate this function for every possible value of y1 and y2, you get exactly the same value. It turns out this representation is not unique. And that's actually going to be an important property that we're going to exploit later when we look at the graph cut algorithm. Now, an important thing to observe is that a pseudo-Boolean function is really just a binary binary Markov random field, and a quadratic pseudo-Boolean function, so a pseudo-Boolean function where you only have at most pairwise terms between the y's, is a binary pairwise Markov random field. All right? Now, why is this important? Because the energy functions that we look at often in computer vision, we can represent as pairwise Markov random fields. So Markov random fields or energy functions with just unary and pairwise terms. And when the variables are also binary, then we can write them out as these pseudo-Boolean functions. All right. Now, a really important property of pseudo-Boolean functions is a property known as submodularity. So some pseudo-Boolean functions are submodular. And this is the definition of submodularity based on sets. So a set function, which is a function from subsets to the reals, is called submodular if when you sum the evaluation of that function on two different subsets, that's greater than or equal to the sum of evaluating that function on the union of those subsets and the intersection of those subsets. Okay, so that's sort of more easily explained, I guess, in this cartoon. So you have these two subsets. If you evaluate the function on those two subsets, that sum needs to be greater than or equal to the function evaluated over the union of those subsets plus the intersection of those subsets. And really what submodularity is doing is it's encoding a notion of diminishing returns, right? It's saying if you imagine this second subset to be just a singleton, one component, one element, it's saying that if I evaluate, if I add that element to the set that I've already evaluated the function on, my function value can't increase by more than if I evaluated the function independently on the original set and that singleton element. Okay? So there's this notion of diminishing return, and our graph cut algorithm is going to need this property to run, right? Now, submodularity, as it's defined, is defined in terms of sets and set functions. It turns out there's an exactly equivalent definition in terms of pseudo-Boolean functions. And so here you can think of the Boolean vector as just encoding whether a particular element is in the subset or not, right? So it's 0 if it's not in the subset, it's 1 if it's in the subset. So there's a one-to-one mapping between these Boolean vectors and subsets. And so a pseudo-Boolean function is called submodular if when you sum the evaluation of that function on two different Boolean vectors, that's greater than or equal to the function evaluated on the OR of those vectors plus the function evaluated on the AND of those vectors. Okay? Now, it turns out that there are a bunch of simple checks that we can use to determine whether a Markov random field or a pseudo-Boolean function is submodular. And so if the polynomial form of the pseudo-Boolean functions, remember there's a unique polynomial form for every pseudo-Boolean function, if that has negative coefficients on all the bilinear terms, so for every term in the function that includes two variables, then the entire function is submodular. It has the submodularity property. Alternatively, if the Posi form, if there exists a Posi form representation where all the pairwise terms have the form of a variable and the complement of another variable, then the pseudo-Boolean function is submodular. Or finally, if you're talking about a Markov random field defined in terms of unary and pairwise potentials, then that the energy function associated with that Markov random field is submodular if this expression holds, right? So when you evaluate the sum of the variables taking different values, that's greater than or equal to the evaluation of the sum when the variables take the same values. Okay, and we can see that through this construction here, the equivalence of those last two conditions. So let's say we have a pairwise term that has this form, right? A very general form where you have values alpha, beta, gamma, and delta for all of the 4 configurations. Well, I can rewrite this pairwise term in this way, right? Where it's the sum of these 4 different terms. So if I perform the sum across this, for this first element here, it's going to be alpha plus 0 plus 0 plus 0, so that gives me alpha. For the bottom right corner, it's alpha plus gamma minus alpha plus delta minus gamma plus 0, so that gives me delta. Okay? So this is exactly equivalent to this, but here what I've got effectively is a constant plus a unary term over my second variable, plus a unary term over my first variable, plus this term here, which only depends on one specific configuration. Okay? So I can write this out in this particular way, and the only thing I care about for submodularity is that this is a valid Posi form, which means that its coefficient is positive. So for the coefficient here to be positive, I need beta plus gamma to be greater than or equal to alpha plus delta, right? Which is to say that the sum of the off diagonals has got to be greater than the sum of the diagonals. Okay, any questions? Okay. All right. So it seems like a long way, but we're making progress towards the graph cut algorithm. And this is the classic graph cut algorithm. So the graph cut algorithm says if we're given a graph defined on nodes V and edges E, which is capacitated, so all of the edges have a capacity associated with the edges, or a weight associated with the edges, and 2 distinguished vertices, or nodes, S and T, then an ST cut is a partitioning of the nodes into an S set and a T set, where the node S has to be in the S set, the node T has to be in the T set, and all of the other nodes have to fall into one of those sets. The cost of the cut is going to be the sum of all the edge weights going from the S set to the T set. So in this case, it's going to be this edge plus this edge plus this edge, okay, is going to be the cost of that cut. The minimum cut problem is to find the cut in this graph. Okay, there are lots of different cuts. Is to find the cut that has the minimum cost. All right, so it's a partitioning of nodes into an S set and a T set with a minimum cost. All right, so here's the main idea of how we're going to use graph cuts to solve our inference problem in a binary Markov random field. What we're going to do is we're going to first construct a graph such that every ST cut in the graph corresponds to an assignment to the variables in our model. Okay, so every partitioning of nodes into an S set and a T set is going to correspond to assignment to the variables. The cost of the cut is going to be equal to the energy of that assignment. And the minimum cut, therefore, is going to correspond to the minimizing assignment. Okay? If I can find the minimum cut in the graph, then I found the minimum assignment to the variables. And this whole construction is going to rely on the fact that the energy function is submodular, because in order to do graph cuts, I need the weights on the graph to be non-negative. All right? So let me show you how we're going to do this. Here's our energy function that we had before. So we had this energy function defined over 2 variables, y1 and y2. It's got these 3 potentials. And so what I'm going to do is I'm going to construct a graph where I have the S node and the T node. And I'm going to denote everything in the S set that falls into the S set as having label 1, and everything that lands in the T set as having label 0. Okay? And then in addition, I'm going to have a node for each of the variables in the model. Right? Now, note this graphical representation is very different to the graphical models and factor graphs that I showed before. Graphs are used all over computer science. Don't confuse one graph for another. So this is an ST graph. Okay? Here's how I'm going to construct it. My first potential function or factor was 2 times y1 plus 5 times y1 bar. So I'm going to add an edge from S to Y1 of weight 5, and an edge from Y1 to T of weight 2, okay? And note, this is completely algorithmic, right? It's just a construction where I read off the weights. And you can note already, if I cut this edge, so I put Y1 in the T set, what I'm doing is I'm saying Y1 takes value 0. That's going to cut this edge here. That's going to cost me 5, okay? Because 5 times Y1 bar, if Y1 is 0, it's 5 times 1 is 5, okay? Same as if I cut this edge here. If I cut this edge here, I'm saying Y1 goes into the S set, so it has value 1, and I get a value of 2 up here, okay? I can do exactly the same thing for the next term. So 3 times Y2 plus Y2 bar. I'm going to add an edge of weight 1 between S and Y2, and an edge with weight 3 from Y2 to T. And then finally, for the last two terms, I add an edge whose tail starts at the non-barred variable and ends at the and whose head terminates at the barred variable with weight equal to the coefficient. Okay, so 3 times y1 bar y2 ends up being this edge from y2 to y1 with weight 3. Okay. So it's a completely mechanical construction. I can give you an energy function in Posi form. You can write out, you can construct the ST graph. Now, let's look at various cuts through this graph. Okay, here's a cut. It partitions the nodes into this T set where Y1 and T are in the T set, and Y2 and S are in the S set. So what that's saying is that Y2 takes value 1 and Y1 takes value 0. So if I evaluate the energy function with those, that instantiation of the variables, I get 5 plus 3 plus 3, 11. And if you look here, I've cut this edge, and this edge, and the sum of those weights is 11. Okay. Now, why didn't I cut this edge, right? Why don't I take 4 into account? Well, the definition of a cut, or the cost of a cut, is the sum of the edge weights going from the S set to the T set. And this is an edge that goes from the T set to the S set, so I don't include its weight. Okay? Is that clear?
Just to check, the designation of which is the S and which is the T is totally arbitrary, right?
Totally arbitrary. So the designation of which is the S and which is the T is arbitrary, and I'll show you a later slide where I flipped S and T, and you get exactly the equivalent construction. You have to flip the direction of your edges, but the algorithm works exactly the same. Okay? All right. Here's an example of another cut. Okay, I'm cutting these two edges. So I'm putting both Y1 and Y2 in the S set, which means they both take value 1, and nothing's in the T set other than T. So that is 2 plus 3, which is 5, and the edges that I've cut, the sum of those edges is 5. And it turns out this is the minimum energy cut, right? Okay, here's an example of something that's not a cut. Okay, it looks like a cut because I've cut these 4 edges, but I haven't partitioned the nodes into 2 sets, an S set and a T set. Here I've actually got 3 sets. I've got this S set up here, I've got this T set down here, and I've got this set in the middle, which isn't connected to either S or T, okay? And so that's not a valid cut, and so there is no instantiation of the variables that will give me this energy of 5 plus 1 plus 3 plus 2, right? Actually, there is, but it's not this assignment, right? So this, don't get confused with cutting edges and valid cuts, which are actually partitions of the nodes. Right. So this goes back to the question over here of, well, what happens if we switched the meaning of S and T? Well, you end up with a graph construction, which is done in the equivalent way, but the same thing happens. Cuts in this graph correspond to assignments to the variables, and the cost of that cut corresponds to the energy value for that particular assignment. So these two graphs actually represent exactly the same energy function. And you can see the only thing that's happened is the direction of these arrows between the nodes have switched, and the weights of the nodes, the edges from terminal nodes, so S and T, have flipped. Okay, so 2 here and 5 here versus 5 here and 2 here. Otherwise, exactly the same. Okay, so let's jump up at the big picture and see where we are. We have a problem in computer vision. In this case, say it's an image inpainting problem, which we formulate as a Markov random field. This Markov random field we're going to write out as a Posi form, okay, and so that requires the variables to be binary. Let's just assume they're binary in this case. Once we have that Posi form, we can construct this ST graph, and if we can find the minimum cut in this ST graph, then we found the optimal assignment to our variables, right? So the question becomes, well, how do we solve this minimum cut problem? All right. Doesn't seem like we're making much progress yet, right? Yes.
This minimum cut is part of the inference. It's not a separation, particularly you see we have to have values of our parameters.
Okay, so the question was, this minimum cut problem, is that just part of the inference or is that the whole inference? Okay, so if this model, I'm assuming that we've already learnt the model, so the model's given, which means that its structure and all of the parameters are given. If we're given this model and it's a pairwise model, so the only terms we have are unary and pairwise potentials, and the variables are all binary, then graph cut is the end of the story. You can do a single graph cut and it will give you the optimal assignment to those variables, assuming it's submodular as well. If any of those conditions are not true, so if the variables are not binary, if you don't have pairwise potentials, so you have higher order potentials, or the energy function is not submodular, then graph cut becomes a component within the inference algorithm. And I will show you how we can use it under those situations a little bit later. Okay? So for now, we're assuming that we have a pairwise binary MRF that is submodular.
Just wondering what the class labels are for this particular problem with inpainting.
Okay, so for inpainting, so the question was, what are the class labels for inpainting? In this case, the class labels would be grayscale values, so a number between 0 and 255. So in this case, it's not a binary problem. But for a foreground background segmentation problem, you would have a binary problem, right? Okay, so yes, I should change the slide if I want to stick to my story of binary MRFs, but you can wrap this procedure to solve these image inpainting problems. Okay. So our question now is how do we solve this min cut problem? And what we're going to do is we're going to flip the problem from a min cut problem to a problem known as a max flow problem. And there's a very, very famous theorem from 1956 which says that the maximum flow from a vertex S to T in a graph, in an ST graph, is equal to the minimum cost of the graph, right? So this theorem came up at a time when people were very worried about operations research and concerned about the Russians building missiles, and so the Americans had to build missiles as well, and they needed to understand things like transportation networks and networks that defined manufacture and so on, right? And so what you can think of max flow as being is, say, modeling maybe a traffic network or a water network where you're sending flow, either traffic flow or water, from some facility to some other facility, right? And you want to know what's the maximum amount of flow that you can send through these pipes or along these roads from one place to another, right, which is defined over this network. Well, it turns out the maximum traffic or the maximum amount of water, the maximum flow you can send is equal to the minimum cut. So if somebody came and sabotaged your network and cut S from T, and they wanted to do that in an efficient way, they'd do that with a minimum cut. That minimum cut is equal to the maximum flow. And so these problems are duals of each other, right? So for us, the important thing is that if we can find the maximum flow, then that also tells us the minimum cut, and that solves our problem. And it turns out there are very nice algorithms for finding maximum flow. So, okay. So I think what we'll do is break there, and then after the coffee break, I will go through the actual algorithms for finding the maximum flow or the minimum cut. Okay, so I think the break is how long?
Yeah, the break is now, and you have till 10 before, and we resume. So
Okay, so
20 minutes.
20-minute break. Terms, we can write it out in as a pseudo-Boolean function in Posi form. Posi form means that we've got these positive coefficients on all of the terms, and we've got both variables and their complement. And then cuts in the ST graph that corresponds to this Posi form representation gives us are equivalent to instantiations of the variables, and the value of that cut is the same as the energy function evaluated on the variables taking those assignments. Now, somebody asked me in the break a question about the edges that go between the y's. Why are those important? These edges that go between the y's are the things that make the model a random field rather than a set of independent prediction models, right? If I didn't have edges in the middle here between the random variables, if I only had edges between the terminal nodes and my variables, then I could just make completely independent predictions, right? If these edges weren't here, maybe I can go back, right? If these edges weren't here, then my prediction of y has no influence on my prediction for y2, right? And so I would just cut this edge and this edge because they're the minimum cuts for those variables independently, okay? So the whole reason we're doing this graph cut is because we're dealing with variables that depend on each other, and the way we encode those dependents in graph cuts is by having edges between them. There's a question up there? Okay, so the question is what happens for non-binary state spaces. I'll discuss that in a sec when I go over the algorithm. Yep. Okay, the question is, shouldn't the edges in a Markov random field be undirected? Good question. This comes back to, again, graphs being used to represent a whole bunch of different things. So when you draw the graphical representation for a Markov random field, you draw it with undirected edges, okay? And that's because there's no causality in the influence of one variable over another. You're just encoding correlation between variables. When you construct the ST graph for inference in the graph of the Markov random field, the ST graph construction has directed arrows, and that's because you're looking at flow that's going from S to T. So these graphs are different things. They're depicting different things. The one is the graphical model graph is showing you the structure of your energy function. The ST graph is merely a representation that we're using during inference to solve the max flow min-cut algorithm. Yes. Okay, so the question is, do you construct a single graph for the entire MRF or for each clique? You construct an ST graph for the entire energy function, MRF, for the particular instance that you're solving. Okay, so you have a model that you can run on a whole bunch of different images. For each image, you construct an ST graph for that image, and the value of the potential functions may change because the potential functions, the value on the edges may change because the potential functions are defined in terms of features from that image, right? There's observations that you make for a particular instance of the problem that goes into the computation of these weights. But once you've done that for a particular instance of the problem that you're trying to solve, you construct a single ST graph for the entire problem. Okay, so for every pixel in the image, there will be nodes in the graph and they will all be connected. I just draw two here for simplicity. Okay, so let's get on with the algorithm. So here's an example of a max flow graph. So we're trying to find the maximum flow through all the different paths from S to T. There's an algorithm known as an augmenting path algorithm. This is a very, very popular algorithm for solving these problems. And I'm going to go through the algorithm now. So we start off over here with zero flow. We haven't sent any flow from S to T. The notation I'm using is I'm going to annotate an edge with the amount of flow that we've currently sent, and C is its capacity, okay? So the capacity of this edge is 5. I can send at most 5 units of flow through that edge. Currently, I've sent 0, all right? And so the way an augmenting path algorithm works is it starts by finding an augmenting path. So this is a path from S to T that has residual capacity. It has all of the edges along that path have the ability to increase the amount of flow that I've sent already through that path, okay? Any ideas for how I would find such a path? Sorry? Maximum weight? No? Okay, I could do a depth first or a breadth first search, right? So I just start here, so I can go either that way or that way, and then from each node I just keep going, right? So an augmenting path is any path with residual flow. It doesn't have to be the path with the most residual flow, residual capacity. Okay? So this is one such path. There could be others. Now, I look at this path and I say, well, how much flow can I send through this path before it gets saturated? Well, I can send 5 here, I can send 5 here, I can send 3 down here. So the most amount of flow I can send through this path is 3, right? 3 units of flow. So I send 3 units of flow through the path. This edge is now saturated. I can't send any more flow through that bottom edge from C to T. And the current amount of flow that I've sent so far is this value up here, 3. Okay? Now, I look for another augmenting path. Okay? Here's another augmenting path. Goes this way. You can see I've got a residual capacity here of 2. I can send another 2 units of flow along this edge. I can send 3 along here. I can send 2 along here. I can send 5 along here. So the maximum amount of flow that I can send through this path is 2, right? So I send 2 through that path. I've now saturated both this edge, and the amount of flow that I've sent currently from S to T is 5. Okay, let's look for another augmenting path. Here's one. This is an interesting one. It goes from S to B, and then B back to A, right? Why can I send flow through this path? Because I've already sent 2 units of flow in this direction. I can take back some of that flow, right? So I can send flow back in the opposite direction, and the maximum amount of flow that I can send in that backward direction is this unit 2. All right? And so I can send, I've got residual capacity here of 2, capacity here of 1, capacity here of 3, and so the maximum amount of flow that I can send along this augmenting path is 1. All right? And so I send 6 units of flow. I now look for another augmenting path. There isn't one. And so I found the maximum flow that I can send through the path, through the graph from S to T. That's got a value of 6. To find the minimum cut, I look at all of my saturated edges. Okay? And I can just cut along those saturated edges. So here's one, and here's one. I could also cut this edge here, but node A is actually connected to S through another path, right? And so it wouldn't actually help me to cut that edge. So if I look at the value of the edges that I've cut, it's 3 plus 1 plus 2, right? So that's 6. So the minimum cut is equal to the maximum flow. Okay? Does that make sense? Is that clear? All right.
When you say, so this is something I looking at you say the maximum flow is equal to the minimum cut. Aren't these two separate classes of things? Isn't the maximum flow an integer in this case and the minimum cut a set of edges?
The cost of the minimum cut. The minimum cost cut. Okay, so the question was, why am I talking about flow, which is a number, and cuts, which are sets of edges? And so when I talk about a cut, I'm talking about the cost of that cut, right? And so the maximum flow is equal to the cost of the minimum cut, okay, or the minimum cost cut. Okay. Yes. No, good question. Okay, so the question was, would I get a different answer if I started with a different augmenting path, or if I chose different augmenting paths? No, you would get exactly the same maximum flow and exactly the same minimum cut, assuming it's unique. Well, the maximum flow is unique. There is one maximum flow. There may be different cuts that are minimal. The difference will be in the running time of the algorithm. So depending on how you choose to find your augmenting paths, the algorithm may take longer or shorter to converge. And if you go onto Wikipedia and you look at, there's an article on maximum flow algorithms, it will show you an example of finding augmenting paths using breadth first or depth first search, and they have very, very different running times. The one sort of keeps just sending 1 unit of flow every iteration on a fairly pathological graph, but yeah, it's got a very bad running time, whereas the other one converges, I think, in 2 iterations.
You cannot have negative flow as an intermediate step.
You can never have negative flow, but you can send flow back through a path.
So the second step you did, where you said like, well, we're at capacity, but we can take one off, that wouldn't be possible to take that as the first path, right?
No, that's right. So you can't send negative flow through the graph, but you can take back flow that you've already sent. Okay, so here's a summary of the augmenting path algorithm. While an augmenting path exists, you send as much flow as you can through that augmenting path, update the edge capacities to produce a residual graph, so a new graph with updated capacities. You keep iterating until there are no augmenting paths, and then you look for nodes. Once you've sent as much flow as you can, you look for all nodes that are reachable from S, so that have a path from S to the node with residual capacity. Those nodes go into the S set. All the nodes that can reach T go into the T set, and that gives you your cut. Now, it's possible that there are some nodes that are cut off completely from the graph, that are not reachable from S and can't reach T. And those nodes can be labeled arbitrarily as 0 or 1, and they will give you the same energy, right? So there are ties in that case. If there are multiple of those nodes that are connected together, then you need to be a little bit careful about how you label them. But in general, that means there are ties in your graph. Okay. Now, there is another algorithm that has some other nice properties. It's called the push relabel algorithm. This algorithm is, in general, slower than the augmenting path algorithm, but it can be easily parallelized, which is why people like it. I'm not going to go through the algorithm. There are slides online which sort of have every step of the algorithm, but just in the interest of time, I won't go through. This algorithm, unlike the augmenting path algorithm, allows for intermediate steps to violate the flow constraints. So it allows nodes to send out more flow than they have currently, or edges to be saturated. But by the end of the algorithm, all of your flow constraints are satisfied. Okay, so yeah, in the interest of time, I won't go through it, but you can see it takes me a lot more clicks to get through this one, right? So the algorithm's slower. That's how you know if an algorithm's slower than another algorithm. Okay, but the point is it gets exactly the same minimum cut, right? And finds the same maximum flow. So the summary for this algorithm is that there are these 2 steps, push and relabel. Again, in the interest of time, I won't go into it. But the important thing, in fact, if there is a single thing that you remember from this lecture, and I hope there's more than one, but it's how the augmenting path algorithm works for graph cuts, and that graph cuts can be used to solve Markov random field inference problems.
Sorry, but it's something that you might have just missed. But how did you pick? You know, after doing your augmented algorithm, what the maximum flow is. How did you pick which edges? Were they just the saturated ones?
The edges I cut were the saturated. Well, they're actually the ones. the way I define the cut is in terms of a partition of the variables. The way I partition the variables is I look to see whether there's a path exists between either the S node and the variable, a directed path, or between the variable and the T node. And there can't be a variable that has a path both from S to that variable and from that variable to T, because that would be an augmenting path and I'd be able to send more flow. Okay? So in this case here, I can reach B directly from S. I can reach A directly from S. Okay? And so here we can already see this is a different solution in terms of augmenting paths to the augmenting path algorithm, which had this edge saturated, but I've got the same result. C can connect to S from via A, and then D has a direct edge with residual capacity to T. So that defines a partitioning of the variables, and then I just draw my cut.
Okay, so when we say this node can be reached, we're saying basically there exists a non-saturated.
There exists a non-saturated directed path from that node to T or from S to that node. Okay. So if you look at the state-of-the-art algorithms for optimizing arbitrary submodular pseudo-Boolean functions, the algorithms run in order n to the sixth, where n is the number of variables in the model. It turns out, though, that for quadratic pseudo-Boolean functions, so for the restricted class of pseudo-Boolean functions which only have pairwise terms, we have these much, much more efficient algorithms based on graph cuts. And these first two, the Ford-Fulkerson and Edmonds-Karp, are augmenting path algorithms. So they work by the algorithm that I showed. The difference in them is the order in which, it's in how they choose the augmenting paths. So the one chooses them by depth first, the other one by breadth first, and you can see that affects the running time of the algorithm. For Ford-Fulkerson, the running time depends on the actual maximum flow, which you don't know but ahead of time, but that's the complexity of the algorithm. The other one is quadratic in the number of edges. Push relabel is sort of worse than these algorithms for sparse graphs, where the number of edges is sort of quite low. But again, it can be parallelized and so is attractive that way. There's this other algorithm which is used everywhere in computer vision. Okay, it was sort of I guess discovered or invented around about 2001. It's got a horrible worst case complexity, so its theoretical running time is terrible. You wouldn't choose it over any of the other algorithms, but it runs amazingly well in practice. And that's what allows us to do inference on like these megapixel images in under a second. And the way this algorithm works, it's an augmenting path algorithm, but it keeps its search trees that it's developed so far for successive iterations of the algorithm. So in a standard augmenting path algorithm, you search for an augmenting path, and then all that work that you did in searching for that augmenting path, you throw away. With this algorithm, you keep those search trees around. And so this is how it works. You start growing these search trees from both S and T. Okay, and so remember I said you can do depth or breadth first search. This is doing, I guess, a mix of them. And at some point, these search trees are going to touch each other. When they touch each other, it means you found an augmenting path. So you can now send flow through that path. When you send flow through that path, you're going to saturate at least one edge, maybe more. Okay, so in this case, I'm saying I've saturated these edges here. And so that breaks these these two connected trees into two subtrees again from S and T, as well as the possibility of some nodes in the middle. Okay, and these are called orphan nodes. When you have this situation of this orphan subtree, you try and find an edge where you can connect that back to one of the trees that you're growing from S and T. Okay, and so in this case, we found this edge here. And so now I can connect this entire subtree up to T again. And then I keep iterating, looking, growing these trees, trying to find a connection. And so the beauty of this algorithm is I didn't have to start my search trees from scratch each iteration. I kept that around. And that allows them allows the algorithm to run really, really fast. Okay? And so if you get any library off the internet that implements graph cuts for vision problems. It's going to implement either that Boykov-Kolmogorov algorithm or a variant of it. Okay, a sort of a nice way to think of these graph cut algorithms is that as the algorithm is running, it's giving you a reparameterization of your energy function, right? So every time I find an augmenting path and I update the edge capacities, it's giving me a new graph. I can read the weights of that graph and I can construct an energy function from that graph. And that energy function is a reparameterization of my original energy function. So it turns out that these two energy functions are exactly the same. If I plug in values for y1 and y2 here, and plug in those same values for y1 and y2 on the second one, I get exactly the same number, okay? And this is because you'll remember that I said the posiform representation of an energy function is not unique, okay? And so these are two posiform representations of the same energy function. They give the same value. The graphs, however, are very different. In this graph, it's quite hard to find what the minimum cut is. In this graph, it's actually quite easy, right? It's going to be this, I cut this edge here, it's a cost of 5. And so this is what the augmenting path algorithm is doing for you in GraphCut. It's moving you from this complex graph structure by reparameterizing the energy function into a simpler graph structure where it's trivial to find the minimum cut. And in fact, I could take this one step further by sending flow of 5 through this augmenting path. That would remove this edge altogether. I would have a new graph, which I could read the energy function of. It's going to be y1 bar plus 2 times y1 bar y2 plus a constant of 5, okay? And that's going to be a posiform representation, which is exactly the same as this energy, these energy functions up here, but where the cut is trivial, okay? And that's sort of a nice insight into these algorithms. It relates what the algorithm's doing back to the representation and the posiforms. All right, so where have we gotten to? Well, we've now shown that we can take our, say, pixel labeling algorithm, we can represent it as a Markov random field, and if it's a binary Markov random field that's submodular and only has pairwise terms, we can use graph cuts to solve the inference problem exactly. Okay, so somebody raised this question before. They said, well, what about multi-label problems? What about non-submodular problems? And what about higher order terms where you have higher than second order functions? It turns out in all of these cases, we have approximation algorithms, but all bets are off in terms of optimality. So we don't have algorithms that will optimally solve these problems. But I'll give you some insights in how the approximation algorithms work. Okay, so if we have a non-submodular energy function, but it's still binary and pairwise, then the energy function doesn't satisfy this condition, which we said we needed for submodularity. Well, it turns out that there are two ways we can handle this problem. The first is that we just ignore these terms, or we modify them in some way so that they're submodular, okay? So it gives us a different energy function. It's not the problem we're trying to solve. Maybe it's close to the problem we're trying to solve, but we can run graph cuts and get an exact algorithm, an exact solution for that modified problem. The other way we can do it is we can relax the problem and solve it using an algorithm known as QPBO, or roof duality. And this relates very much to linear programming relaxations. I'll just briefly go through each of these two steps, but in the interest of time, I'll sort of ignore the details. Okay, so the first way we said we could deal with non-submodular terms is to replace them with something that's submodular, but in some sense close to the non-submodular one. The way this is often done is if we have a non-submodular potential, okay, on a previous slide I had alpha, beta, gamma, and delta. Here it's A, B, C, D. If it's non-submodular, it means that we have this condition holding. What I can do is I can adjust all of the terms, A, B, and C, by this amount delta over 3 to bring the pairwise potential or to project it onto the space of submodular potentials, okay? And so I'm modifying the terms, but I end up with an energy function that's submodular, and then I can run graph cuts. The other way we said we can do it is through this algorithm known as roof duality. So the way roof duality works is I have this pairwise energy function, and I can break up my pairwise terms into those that are submodular and those that are non-submodular. For the, Then what I do is I introduce these duplicate copies of the variables, right? And these are negated copies, right? So the same way as when I constructed my ST graph, I had these negated copies of the variables. I can now do that by writing these variables directly into the pairwise terms of the energy function, okay? And so what I've done is I've just split the various potential functions into two parts, one which takes the original variable and one which takes its negated copy. And so 1 minus the negation is the same as the original variable. And I'm putting half the potential value in one and half the potential value in the other, right? Which is why I divide by 2, okay? So I haven't done anything particularly tricky yet. I've just written this in a different form where I now have these negated copies of the variables. And if I enforce the fact that these negated copies are true negations, right, so that y1 bar is 1 minus yi, then this is exactly the same energy function as before. But what I can do, okay, so the observation is that if yi is equal to 1 minus yi bar, then the original energy function is exactly the same as this modified energy function. But what I can do now is I can ignore this. The other observation is that if I look at the energy function defined over all of the variables, so the original plus the complement, that energy function is submodular, right? So now what I can do is I can ignore this first constraint that says that these variables that I introduced are actually complements of my original variables, and I can solve this submodular problem, right, in twice the number of variables. If when I get my solution, I look at these pairs of variables and that complementary condition holds, that yi bar is 1 minus yi, then I know that the labeling for that variable is optimal. If that condition doesn't hold, then I have an inconsistent labeling. I have my original variable telling me I should label it one way, and the complement of that variable telling me I should label it with the same value, which means I should label it the other way, right? So the solution is inconsistent, and then I have to choose one or the other, right? And so I project back from this approximate solution onto a valid solution, but that's not necessarily optimal, okay? This condition here is called partial optimality, and it's nice in that you know that if some of your variables agree, the complement and the original variable agree, that every optimal solution to your problem has that instantiation for that subset of variables. And for the other variables, you need to do some other procedure to label them, okay? All right, so that's how we deal with non-submodular binary pairwise MRFs. For MRFs that are multi-label, we can do one of two things. We can either transform them into a binary problem, which is exactly equivalent, by encoding the multi-label in a particular way, or we can do what's called a move-making algorithm, where we solve a sequence of graph cut problems to move towards an optimal or close to optimal solution. So I'll give an example of the first case where we have a multi-label problem, but we have a property of the pairwise term where the pairwise term is defined as this convex function over the difference between the labels of the two variables, okay? If that property holds, then we can transform the multi-label problem into an equivalent binary labeling problem using this particular encoding. So I introduce these new variables, right? Let's say I have a multi-label problem where each variable can take four different labels. I'm going to introduce these three new binary variables. And I'm going to encode y equals 1 as this vector 0, 0, 0. And y equals 2 as a vector 1, 0, 0. Y equals 3 as the vector 1, 1, 0. And y equals 4 as the vector 1, 1, 1. Okay? So note, this isn't the same as the binary representation of the label. It's a different encoding. But what it allows me to do is it allows me to construct an ST graph where I can exactly encode these particular types of pairwise potentials. Okay? And again, in the interest of time, I won't go into the details, but if you're interested in it, have a look at this paper here by Ishikawa. Okay? The take-home message, though, is that some multi-label problems can be converted exactly into binary label equivalents, just with more variables. The other probably more important class of algorithms are these move-making algorithms. So here we have a multi-label problem, and I want to be able to solve that problem using graph cuts as a step within the algorithm. And the way these algorithms work in general is that I start from some solution, some instantiation of my variables, which is a valid assignment. And then what I do is I restrict the search space for some or all of the variables, and I find a new assignment within that restricted search space, which is the best assignment that I can find with respect to my energy function in that restricted search space. Okay? So I take a subset of the possible labels for each variable. I have this new energy function, which is now defined over this subspace of possible solutions. And I find the optimal assignment for the variables given this restricted energy function. Right? The picture to keep in mind is I have some solution, existing solution. Given that solution, I define some restricted search space around it that includes that solution. It's not the whole space, it's a part of the space. And then I find the best solution I can within that subspace. Okay? And then I can keep iterating. I now have a new assignment. I define a restricted search space around that new assignment, and I keep iterating, and hopefully I end up hitting this true optimal solution. I may not. Yes? Okay, the question is convexity important in the subspace searches? The way I've defined it here, no. So this is a completely general algorithm that even the optimality here is not required, but for the purposes of this tutorial, let's say it is. The only thing that you require is that within the restricted search space, there exists an algorithm that allows me to find the optimal solution within that restricted search space efficiently. Okay? And so what we're going to look at is we're going to look at restrictions of the search space that result in submodular binary pairwise Markov random fields. Okay? All right. So, really the only important thing here is that at each iteration you're finding a new assignment that has a lower energy than your previous one, and you keep going until you can no longer find a lower energy assignment, and then you've converged to a local optimum. All right. The most simple version of a move-making algorithm is an algorithm known as iterated conditional modes. And this was, I guess, formalized in 1986. It was probably known well before that. Okay, so here in this problem, we're going to reduce the multivariate, multi-label problem inference into a series of univariate inference problems, which we can solve very efficiently, right? We're only doing inference over a single variable. Okay, how do we sort of formulate that in this move-making way? Well, for each move, we choose one of the variables, say yi, and we set the space the label space for that variable that we're going to search over as the entire label space, right? So every possible value that particular variable can take. For all of the other variables, we fix its value to its existing value, right? The value that we've initialized it at. Okay, so now we've projected our energy function from this multivariable function to a univariate function. We just search all possible values for yi, and we pick the best value. Okay? And then we go and we choose another variable and we optimize over that variable. Okay? It's a greedy algorithm. It's very simple. Performs horribly. Right? Gets stuck in local optima very quickly, but it's nice and general and can be applied to arbitrary energy functions. A more sort of useful class of move-making algorithms are the so-called alpha expansion and alpha beta swap algorithms, which make use of graph cuts as their inference step. Okay? And so here what we're doing is we're reducing the multi-label problem to a series of binary submodular inference problems. And we can do that in one of two different ways. So for alpha expansion, we choose some particular label alpha in our label space. Okay? So let's say we're doing a semantic segmentation problem. Every pixel in the image can take a whole bunch of different labels. We say, for this particular move, for this iteration, I'm going to choose my label as sky. Right? And then what I do is I allow every variable to either keep their current assignment or to take this new assignment alpha. Okay? So they can either stay what they're currently labeled as, or they can be labeled as sky. That gives me a binary labeling problem. Right? The problem is now reduced to a binary problem of stay with your current label or take a different label, right? The label alpha. If the pairwise potential has, for the multi-label problem, has this property that's known as the metric property, then the resulting move ends up being a submodular move, and I can use graph cut. Okay? And so all metric means is this is a valid distance metric function, right? So you're taking the problem, you're casting it as a binary problem, and then your move is to find the best labeling of the variables in this binary problem, and that gives you a new solution to your multi-label problem, and then you keep iterating over all possible values of alpha. The other variant is known as alpha beta swap, and in alpha beta swap, what you do is you choose two labels, alpha and beta. Okay, so I'd say, for this particular move, I'm only going to consider sky and grass. Then for every variable which is either currently labeled as sky or grass, I'm going to allow it to either keep its labeling or switch to the other label. For all the other variables, so the ones that don't take sky or grass, they're going to be fixed to their current assignment. Okay, so I'm allowing alpha and beta to swap. Again, here, if your original pairwise potential function is semi-metric, then when you project down onto this binary space, you end up with a submodular function, and you can use graph cuts to find the optimal move within that search space. Okay? So here's an illustration of how we would do this projection onto binary terms for the alpha expansion case. So for each variable, yi, I'm going to allow its next assignment to be either the previous assignment to that variable or this new value alpha. Okay? And it's possible that these are the same, but then that just reduces to, you just remove that variable from the move. And so what I'm going to do is I'm going to define an energy function over these new auxiliary variables that I'm calling t. And I'm going to say, well, if t takes value 1, then I'm going to keep my previous assignment. If t takes value 0, then I'm going to switch to alpha. And so that allows me to take my unary and my pairwise terms, which are defined in the multi-label space, and project them onto these binary unary and pairwise terms, okay, by just copying the values out. Does everyone see how that works? Right? And so now I have this pairwise energy function. Here are the gory details. It's defined in this way. But this is an energy function now defined over t. And so it only has unary and pairwise terms, which take binary values. I can use graph cuts to find the move. Okay. Is there any questions on alpha expansion in particular? No? Okay. So finally, I want to address the question of higher order models. We've talked a lot about pairwise models, which are a very important class of models, but higher order models are also important, and it turns out that for some higher order models, we can still do efficient inference. So one method we have for dealing with higher order models is known as order reduction. So it turns out that if you have a pseudo-Boolean function where you have a product of terms, product of variables, and a negative coefficient in front of that product, then you can replace that with this construction here where we introduce an auxiliary variable z, and we replace this product as the sum of the negated, or the complement of those variables times z, minimizing the expression here over variables y is equivalent to minimizing this expression jointly over y and z. Okay? The key difference is that here we have an expression which only consists of order 0 and order 1 terms, right? So quadratic terms at most. Whereas here we have an expression which consists of much higher order terms. And so, and the other thing is this expression here is submodular because it includes variables, or it includes terms that only have a variable and the complement of another variable. And so I can use graph cuts to solve this problem. All right? So this is very nice. If you have an energy function which has terms like this, you can rewrite it as an equivalent energy function over binary, over quadratic terms. The other class of higher order models are models which have a particular form, right? And the only one I'm going to tell you about are these lower linear envelopes, mainly because I've done work in this area. And so it turns out that if you have a function, a higher order function that's defined over a clique of variables, and the way it's going to be defined is as a lower linear envelope. I should have included a plot of this. But this is basically a set of linear functions which are defined by the number of variables within the clique that take assignment 1. Then each of these members of this set is a linear function, and I'm taking the minimum of those, so I'm taking the lower envelope. If I have a higher order function defined in this way, then similar to the construction here, I can decompose it as a telescoping sum, where I have my first linear function, and then I have the sum of the difference between successive linear functions multiplied by this auxiliary variable that I introduce. Okay? Question?
Yeah, sorry, just throw us back to the graphs. So what does a higher order model MRF look like? What's the difference?
Okay. So the question was, what's the difference between a higher order MRF and a pairwise MRF? A higher order MRF has terms which are defined over more than 2 variables. So it could be 3 variables, it could be 1,000 variables. Okay? In a pairwise MRF, you only have terms defined over individual variables and pairs of variables. No, it could be a grid. So you could have 4 variables, and you just have pairwise terms defined between the 4 variables, but they're still pairwise terms. Whereas in a higher order model, you put all of the variables into one function, and you can't necessarily decompose that as the sum of pairwise terms. The reason this might be useful is you may have some information that says all of the pixels within a particular part of the image should be labeled with the same label. And so you could encode that by having a whole lot of pairwise terms that says, okay, between every 2 pixels within this region, you should label them the same. Or you can have one of these higher order terms that just say, you know, I would prefer for all of these pixels to be labeled the same. Okay, so it turns out that if you do this construction here, you introduce these auxiliary variables z. What these variables are basically doing as you turn each of these variables on in succession, is they move through the different linear functions that you could choose in this family, right? If you minimized over k. And so now there's a mapping between these auxiliary variables z, which are binary, and the k that you choose as the minimizing as the minimizing k, right? And if you sort of stare at this for a little bit, or substitute these functions fk down here, you'll notice that you end up with these pairwise terms between z and y, and so again you have a pairwise binary MRF. Okay, so the last part of the tutorial, I wanted to go through two things: relaxations and dual decomposition, which is another very important inference algorithm. And then last night I stupidly thought I'm going to have so much extra time, and I added a whole other section on learning. So let's see how we go. I think we'll get there. But if I'm going too fast, just slow me down and ask questions, and we can skip the learning. Okay, so we've covered move-making algorithms, we've covered graph cuts. This is the last sort of family of algorithms that are very useful for inferencing graphical models, and they're based on a mathematical programming formulation, so an optimization formulation. Okay, so I'm going to change notation a little bit, and this could get ugly. But I'm going to define these parameters, theta, which are going to be indexed by the clique and an assignment to the variables within that clique. And I'm basically going to set that to the value of the clique potential if I evaluate it on those assignments. Okay? And then for all of my variables or subsets of variables, I'm going to introduce this indicator vector. Okay? So the indicator vector is going to take the value 1 if the variables in the clique C take assignment YC, and it's going to be 0 otherwise. Okay, so there'll be an example, I hope, later on, which makes this a little bit more clear. What this is going to allow me to do, though, is it's going to allow me to take this energy minimization problem that I've been talking about for 2.5 hours and rewrite it as a mathematical program, right, as an optimization problem. And so the optimization problem is going to be to minimize over these indicator vectors the inner product between these parameters and the indicator vector, subject to a bunch of constraints. Okay? The first constraint is that these indicator variables are binary. They either take label 0 or 1. That the sum over all possible instantiations, all possible labelings or configurations for a subset of variables for the indicator variables associated with our clique is equal to 1. Okay? This is a mathematical way of saying that you need for one of the indicators to be 1 and the rest to be 0. Right? It's basically saying if I have a particular set of variables, there can only be, the indicator is 1 for a particular configuration of those variables, right? And 0 for all the other configurations. And finally, this last constraint is saying that if I have the same variable that appears in 2 subsets, in 2 cliques, then I need to my indicators need to be consistent, all right? It's a little bit confusing here. It's going to be simpler if we just look at an example. So again, we go to our favorite example of the 2-variable model. So here I'm going to write out my weight vector or parameter vector as the values for each of the particular clique potentials, right? So here are the values for the first clique potential, either taking value 0 or 1, the second one, and the third one over the 2 variables. And then here's my indicator vector, right? And if I write out all the constraints, I sort of have these constraints here. So this first constraint is that saying my indicator vector for y1, taking value either 0 or taking value 1, if I sum those up, I must get a value of 1, right? So one of these has to be 1 and the other one has to be 0, which says that y1 needs to either take value 0 or needs to take value 1. It can't take both, it can't take neither. Okay, was there a question? Nope. Okay, so let's look at a particular example. If y1 took value 1 and y2 took value 0, then my indicators variables would look like this. This variable here is telling me that y1 takes value 1, set to 1. This variable here is telling me that y2 takes value 0, so it's set to 1. And this one down here is telling me that y1 takes value 1, and, okay, I've really confused things here. 1 and 2. I've swapped these around. Okay. This should be 1, 1 and 2, 0, right? Has that really confused everyone? Right. It's right? Oh, sorry, yes, you're right. Okay, I've just confused myself. Good, okay. Am I the only person in the room confused? Yes, good, okay. Yes, so this is saying that variable y1 and y2 takes value 1 and 0, and so that's set to 1, okay? And so now if I take the inner product between this vector and my parameters, I end up with the correct thing, right? It's the first factor evaluated at 1, the second factor evaluated at 0, and the third factor evaluated at 1, 0, okay? So we now have this optimization problem, but it's slightly difficult to deal with for two reasons. One, the first reason is that we have binary variables, and so they're difficult to optimize over. And the second problem is that we have a whole bunch of these constraints that define something called the marginal polytope. And the marginal polytope you can think of as this this subspace which defines valid solutions. So solutions where my indicator vectors are in agreement with each other, right? In particular, this pairwise indicator vector agrees with the indicator variables for the unary case. All right. This marginal polytope is tight if the factor graph is a tree, right? And this shouldn't be surprising because what this is sort of saying is that the message passing algorithms that I developed before, which were exact, allow me to exactly solve this problem. And what this is saying is that I can exactly express all of the constraints that I need to satisfy in an efficient way. For cyclic graphs, this marginal polytope may contain fractional vertices. And what that means is I may end up with solutions that, or assignments to the indicator vectors that aren't consistent with each other, right? So approximations. And then another interesting thing about this marginal polytope is that for submodular energies, even though the polytope, so the set of feasible solutions, contains fractional solutions, they're never optimal, okay? And so that's why algorithms like GraphCuts gives us optimal solutions. All right, so let's go very quickly through how we then do dual decomposition. So I start with this binary integer problem, which I've said is difficult to solve because of these constraints on the variables that require them to be binary. I'm going to relax those constraints to be linear constraints. So I'm going to say instead of the indicators having to take a value of 0 or 1, they can take any value in the range 0 to 1. But I'm going to keep these other constraints around which say that the indicators have to sum to 1 and that they have to agree to each other. So now I have a linear program which I can solve. It will give me an assignment to these indicators, but they may not be 0 or 1. And so I'm going to have to round those, the solution I get from my linear program to a 0, 1 solution and get an approximate solution to my algorithm. Typically, if you use standard LP solvers, these problems are way too big to express in a standard package. And so people resort to coordinate descent on a dual formulation of the problem, right? And as I said, the solutions will need to be rounded. Okay. Yep. Yes. So the question was, if you have solutions that need to be rounded, and you round the solution, you may get a much worse energy. And that's true. So you end up with a relaxed solution, which is not feasible in terms of the original binary problem. You project that into a feasible solution, you may end up with a horrible energy. That's true. It turns out, though, that for a lot of problems, that's not the case. You end up with a very good solution. And you could do things, there are techniques that people use for how to do more intelligent rounding to get better solutions. Okay. Okay, so I'm going to quickly go through how to take this primal form of the problem and represent it in a dual form that has a very nice algorithm known as dual decomposition or Lagrangian relaxation for solving that algorithm in a distributed way. Okay, so the first thing we do is we write out our problem where I've now written my original energy function, which was the dot product between this very large parameter vector and indicator vector, as the sum over the parameters for the individual cliques and the indicator vector or variables for that clique. Okay? And what I'm going to do then is I'm going to pad out this smaller parameter vector to have a whole lot of zeros and just multiply that by the full indicator vector. Okay? Does everyone see what I've done? No. Okay, let's go back to here. So here I have indicators for the first clique, indicators for the second clique, and indicators for the third clique. So I can write out the dot product between mu and theta here as the sum of three dot products between mu for just the first clique and the parameters for the first clique, mu for the second clique and the parameters for the second clique, and mu for the third clique and the parameters for the third clique. Then what I can do is I can say, well, the problem is I've now got a whole lot of these smaller indicator vectors. I want to just write it out in terms of this original indicator vector. So for each of these, I can take the original indicator vector and I can construct a parameter vector which for the first indicators has the parameter values here and 0 for the rest. And then for the second one, I have zeros here, the values for those parameters and 0 for the rest. And then the third one, these top ones are zeros and the values are valid there, right? So when I add all these things together, I reconstruct this parameter vector. I'm just writing out as the sum of three different parameter vectors. Okay, so that's what I'm doing here with this theta c tilde. So now the last step is I'm going to introduce copies of mu. So for each clique in my model, I'm going to introduce a completely new copy of all of the indicators. And so I now have the inner product for each clique C of the parameters for that clique times this copy of the variables. Because it's a copy, I want to enforce this constraint that the copies agree with each other. And now I'm optimizing over not just the original variables, but all of these copies that I've introduced. Okay? So again, a lot of my talk today, it seems like we're not making progress, right? We're sort of making the problem a lot more complex. But it turns out that by doing this, I can decompose the problem. So my primal problem in this form that I've written it as is to optimize over all of the original indicators plus their copies in this form. And I can write out the Lagrangian for this optimization problem by introducing Lagrange variables lambda c for each of these equality constraints. Okay? And so that gives me this Lagrangian where I have my original objective plus lambda c times my equality constraints, which I can now, by rearranging terms, write out in this way. Okay? So I've moved lambda c from here to be added together with the theta c, and that's multiplied by the copy of the variable, plus this additional term at the end, which only involves the original variables. Okay? So now forming the dual function, I want to maximize over my dual variables, my Lagrange multipliers, of the function where I've minimized over my primal variables. And it turns out that for the solution to be valid, I need the sum of the lambda c's to equal 0, and that comes from the constraint on this last term here. Okay. So the important thing to observe, though, is that now I'm minimizing over the set of copies of all of my variables, but each copy only appears in one of the terms in this sum. And so the same trick that we used in message passing applies here. I can push this minimization into the sum. And so now, instead of minimizing over a sum, I'm summing over a minimization. And what this allows me to do is to minimize independently over each of these copies of the variables. Okay? And so this is just writing it out again in the original functional form. So here I have my original factors defined over variables y, c. I'm writing my Lagrange multipliers as these functions. This is exactly equivalent to this vector form that I wrote up here. Okay. Right, any questions? Yes.
But the constraints, they are not independent, right?
Right, yes.
So, is it a problem?
Yes. Yes. So the question was, in the constraint, they're not independent. The constraint ties things together. But here they're independent. So given a fixed value of lambda c, I can solve this problem independently. But the lambda c's are tied. Okay. But it turns out that for any value of lambda c, this gives me a lower bound. So the minimum assignment of the energy function is greater than or equal to the sum of the energy function minimized over these copies of the variables, right, over the subset of the variables, plus this component that I get from the Lagrange multiplier. So if I can somehow maximize this lower bound, then that's hopefully going to give me a good solution, okay? And so that's what the dual objective is doing, is it's maximizing this lower bound on my energy function, which I've written in a way that allows me to solve each part tractably. All right. We've got 5 minutes left, so I'm going to skip over subgradients and just move to the punchline, which is how dual decomposition works. Okay, so dual decomposition is a method that's come out of it's come from the optimization community. It was known for a while. It was sort of introduced into computer vision in 2010. And it's this way of breaking up a master problem, which is an inference problem on your on your complete energy function, and solving it by iteratively solving slave problems, which are defined over cliques of your energy function. And the way it works is you create a slave problem for each clique. You initialize your Lagrange multipliers, or your dual variables, to 0, and then you go in this loop where each of the slaves solves its own problem. So it minimizes over its subset of variables this expression here, the clique potential plus the information it got from the Lagrange multipliers, the messages. Okay. You need to be able to do this in a tractable way for dual decomposition to work, and if you can write down your model, you can normally do that, because this is a clique potential or a factor over a subset of variables, and these Lagrange multipliers are usually defined over just single variables. Okay. So each slave can solve this problem. It gets the optimal assignment to the y's, which is the same as the optimal indicator vector. And then the master updates the dual variables by this very simple expression, right, where it takes all of the messages from the slaves, so all of the solutions that are coming from the slaves, it combines them together in a way that tries to get the slaves to agree. Okay, so if one slave is saying that a variable yi should take a particular value, and another slave is saying that that same variable should take a different value, then the master is going to update the dual variables to try and get them to agree, to get the first slave to try take the other value and the second slave to try take the first value, okay? And that's what updating these Lagrange multipliers does. And you keep iterating around this loop until you converge. And you're guaranteed to converge. The dual variables will converge. You're not guaranteed to that the integer solutions will agree with each other, but you're guaranteed to converge to a relaxed solution which you can then round, okay? So in a nutshell, that's how dual decomposition works. Any sort of questions of that? I realise I've skipped over a lot of the details, but hopefully at a high level that makes sense. Mark, okay.
So is C a penalty parameter? Is this from smooth?
This C here?
Yeah.
This is the number of cliques. So that should probably be, the size of, it's the number of slaves. It should be N. So basically what you're doing is you're averaging your solution. You're subtracting the average of your solutions from the solution for each clique. And, no. So what this is doing is it's projecting back onto the feasible set of dual variables. So this is unlike the C parameter that you get in a learning problem, in a structured prediction learning. This is merely removing the average of your indicators in order to project back onto the feasible set, which says that the sum of the indicators has to equal 0. Alpha here is a step size parameter, and there are smoothing parameters if you look at proximal methods of this algorithm, which will make sure that at each iteration you don't jump too far away from the previous one. But in this expression here, there's no smoothing or weighting of your steps other than the step size. Okay, so I'm going to skip over learning. I'm sorry, but if you're interested in it, I'll be around for a while, and we can talk a little bit about learning the parameters. I just wanted to put up a summary of the important sort of take-home messages from this tutorial. So the first is that structured prediction models or energy functions are just pervasive in computer vision. A huge amount of computer vision relies on these models. Even deep learning, which I think you're going to hear about next week, which is sort of taking computer vision by storm, you still have these structured models on top of deep learning models. In computer vision, we're often interested in finding the energy minimizing assignment, so not a distribution at the end, but a single assignment to the variables. There are exact and approximate inference algorithms that we can use based on either message passing, graph cuts, or dual decomposition. I didn't talk about parameter learning, but if you're interested in it, there's if you generalize support vector machines, you can come up with a very similar algorithm for learning the parameters of energy functions from data. It's called a max margin algorithm. And finally, there's still a lot of research to do in both these areas, inference and learning. And so if you're starting your PhD and you're looking for topics in this area, there are tons. Okay, so finally, I'm happy to take questions now or after the lecture, or if you want to, you can email me at the email address below. Yes?
Do you interpret the solution of the penalty relax problem as probability, or the product coefficient of that as probability, instead of having these especially for the volume equation?
So you can interpret, depending how you formulate the problem, you can interpret the solution as min marginals, but they're not really probabilities because they may not agree with each other.
More meaningful, so like determining like in some way to describe the uncertainty in satisfying that pixel.
Right, okay, so the question was that if you get a fractional solution, does that in some way encode uncertainty in your labeling? And yes, it's what a fractional solution is doing is it's basically telling you that there's possibly two different labelings for that variable that could give you an optimal solution, right? And so a classic example is when you have a binary problem and your indicator vector comes back as 0.5, 0.5, right? So it's sort of telling you, well, I could either label this variable as 0 or 1. Both those labelings may be in an optimal solution, but in order to find that optimal solution, I need to make sure I label all of the other variables consistent with that one. And so that's the problem, is that all of the variables are in some way tied to the other variables. And so you have to, when you decode, when you round these solutions, you have to round them consistently to ensure that you're getting an optimal solution. And that rounding is NP hard to do in general.
So isn't that enough for people to consider that as the original problem instead of having this binary set from the beginning and then relaxing to that?
Okay, so the question is, isn't that enough or more meaningful? Maybe we should take this offline, but I will say you don't know which variables are going to give you fractional solutions ahead of time until you've run the inference problem. So in the same way that the QPBEO algorithm works, which I briefly touched on, some of the variables you'll get will have integer solutions, some will have fractional solutions. What you can then do is take the set of variables with fractional solutions and search over those while keeping the other ones held constant. And so it reduces the complexity of your problem, but you don't know how to reduce it until you've solved the original problem, right? And even then, you may end up with an NP hard problem. I mean, you can't get around the fact that the problem is NP hard. Okay, I better take other questions, I guess, after.
Yeah, okay, so let's thank Stephen again for his awesome talk.